So what is the gradient vector of a function of three variables? What is it capable of telling us? Well, typically when we study functions of three variables in a multivariable calculus class like ours, it is very often for the purposes of studying different kinds of surfaces other than surfaces which are graphs of functions, right? Surfaces which are graphs of functions always have to pass a vertical line test, but surfaces which are not the graph of functions don't have to pass the vertical line test. So I could have, for example, let's say f of x, y, z equals 2x squared minus y squared plus 8z to the fourth, or something like that. So there's an example of a function of three variables. And if I want to turn that function into a surface, what I want to do is set the value of that function equal to a constant. In other words, look at a level set of this function. So I'll take the equation f of x, y, z is equal to 1. And in GeoGebra, I have to put that on the other side of an equal sign. F of x, y, z minus 1 is equal to 0. And if I do that, so if I look at a level surface, a level set of a three-variable function is going to be a surface in three-dimensional space. So this is the level surface associated with the function 2x squared minus y squared plus z squared. And it's the surface where the constant value of that function is equal to 1. And so a good question would be then, what do I get if I take a gradient vector of the three-variable function? What should I expect that gradient vector to be able to tell me? So let me pick a point that's on this surface. Let's see, can I actually pick out a point that's on this surface? How about 0, not 0, 1, 0, but 0, 0, 1? Yeah, a point right there that is on the z-axis, so that's a point on my surface. And let's compute the gradient. So the x component of the gradient is going to be the x partial derivative of this function, and that's going to be 4x. The y component of the gradient is going to be the y partial derivative, which is minus 2y. And the z component is going to be the z partial derivative, which is 2z. So my gradient vector for this three-variable function is going to have components 4x, negative 2y, 2z. And let's take a look and see what we would get if we visualized a vector that has its tail at the point P and which has its direction given by the gradient vector at P. So F1 applied to P, F2 applied to P, and F3 applied to P. There we go. So what do you notice about the relationship of the gradient vector of this three-variable function to this level surface? When we were studying functions of two variables, the direction of the gradient vector, because it was the direction of the greatest increase of our two-variable functions, it was also perpendicular to level sets of that function. And so for three variables, we can define a level set of a three-variable function, but a level set of a three-variable function is going to be a surface instead of a curve like it was for two-dimensional functions. But then the gradient of that three-variable function appears also to be perpendicular to that level surface. Right? So it points directly outward, as you were saying before. Right? And so if I move this point around, which I think it lets me do, if I move it around on the surface, then it's still going to point perpendicular to that surface at whichever point that we place it. And so one of the things that having a level surface actually is going to make it a little bit easier to do is if I want to find an equation for a tangent plane to a level surface like this one, what could I use as a normal vector to the tangent plane to this surface? If I'm looking for a normal vector to a tangent plane to a surface, I'm looking for a vector which is perpendicular to the tangent plane to that surface, which is what we mean when we say perpendicular to the surface itself. But that vector is just the gradient vector. Mm-hmm. And so that's the good news about a function of three variables. Its gradient vector, because it's perpendicular to the level surfaces, the level sets of a three-variable function, that means that the gradient vector is exactly also a normal vector to a tangent plane to the surface. All I need to do to find a normal vector to a tangent plane to a surface when I've expressed that surface as a level surface of a three-variable function, x, y, and z, equals a constant, is just to take that gradient, right, which has 3 components. That gradient is going to be a normal vector for a tangent plane to a level surface.